Hello everyone and welcome to my channel. Today we're going to talk about Bayesian analysis. We are also going to talk about how to carry out Bayesian analysis in R. What is Bayesian analysis? Bayesian analysis is a statistical method that combines prior knowledge, which is prior probabilities, with observed data, likelihood, to update beliefs and provide posterior probabilities. The keynotes here are 1. Prior. So prior simply means initial belief about a parameter. Then we talk about the likelihood. The likelihood, the functions, are information from the observed data. Then posterior. So posterior simply means the updated belief after combining the prior and the likelihood. When to use Bayesian analysis. So we make use of Bayesian analysis when we know the prior knowledge or belief about the parameter, or when we want to update our beliefs as new data becomes available. Also, when we need to explicitly quantify uncertainty. Then also, when the sample size is small and the traditional method may not be reliable. So now, a typical example of when to use a Bayesian analysis is, let's have a scenario. Let's say we are evaluating effectiveness of a new teaching method, and the objective is to determine if the new teaching method improves student scores compared to the traditional method. This is what we are going to be using in our analysis in R. So take note. Now, what are the approach? The first one here is the prior. So these things are the things, and this is how we're going to write our codes in R. So for the prior, taking into account the scenario, is based on previous studies. There is a belief that the new method may improve scores by 50%. So this is a prior knowledge. Then the data of which we are going to use for the analysis is a data involving test scores from 100 students. We have 50 students where the teaching method was a traditional teaching method, and the other 50 a new teaching method were used on them. Then the posterior is to combine the prior and data to estimate the probability of improvement. Steps for Bayesian analysis. The first one here is to define the prior distribution. The second one, to specify the likelihood function. The third is to use Bayesian theorem to compute the posterior distribution, and after which we interpret the posterior, which is the probability of improvement. So for this tutorial, we would use R. So what are the advantages of Bayesian analysis? 1. It incorporates prior knowledge into the analysis. 2. It provides probabilistic interpretation of the results. 3. Flexible and suitable for complex models. Number 4. It is effective with small sample sizes. Number 5. It updates beliefs as new data becomes available. So quickly, let us go to R to see how we can do this in R. So this is my R. I am having codes we are going to use for this analysis here under my notepad. So before we go to R, ensure that you have downloaded and installed JAX from this source here, sourceforge.net. You can go there and install JAX. JAX simply means just another Gibbs sampler. So you go and download and install it in your PC before loading your R Studio if you have one, or your R. So after which we install these packages, RJAX and Coda. So RJAX here simply allows R to connect with JAX for Bayesian analysis. And the coder here is used for analyzing and visualizing the results of Bayesian models. Okay, so I will just copy this into my R Studio, paste it here, and run this. So we install it. I have installed this already in my PC, in my R Studio. So what I'll do here is to load it. So load it using this function, using this code here, then Control Enter to load both of them. So you can see here from the console that it is linked to JAX, and you load this as well. Alright, so after doing this, I would now import my data. I would import my data. So this is the code here to import my data. Read.csv, choose.files. Alright, so here, what you see here, this particular function here is to tell R to treat blanks, okay, or NA, if that exists in your data, as missing. Okay, so that is what this one is telling R to do. So I'll just click Ctrl Enter. So my data is saved under my desktop. Okay, so I will just bring it up. So Bayesian Analysis data set, and click Open. So here it is saved in R here. So we're having 100 observations and 4 variables. So I can decide to check out these variables, okay, to see whether it is properly imported. So let's look at it and see it. Control Enter. So look at it. So I'm having groups, pre-test score and post-test score, the student ID. Okay, so the most relevant here are the group, pre-test score, and the post-test score. All right, so having done that, I would now define the Bayesian model. So there is a code for this. So this is the code. I would copy this code. Then what I will explain details of this code. So copy this and go to my R. All right, so from this we can see that first our likelihood was defined here. Our likelihood was defined. We're having the post-test here, and which is called the response variable, and it follows a normal distribution here. And here follows a normal distribution with mu equals to I, and we have tau. Tau is for precision. All right. So now our mean here is also modeled. Look at it as a linear relationship. So we're having beta naught, beta 1, and beta 2. So these beta 1, beta naught, beta 1, beta 2 are just regression coefficient. All right. So this is the likelihood, and down here you see priors for regression coefficient. So we model the likelihood and now the priors. Now we're having beta naught, beta 1, and beta 2. They all follow normal distribution. All right. So we're having here mu, which is mean here, as 0, and we are having the precision here, which is 0.000, which is very low. Okay, so now we are also, after that, we also model for the prior for precision here. So tau simply means the inverse of variance. So get 1 over variance, and tau follows gamma distribution here. So now basically the model, this model, like we said earlier, Bayesian model needs priors and likelihood to estimate posterior distribution for model parameters. So after this, we click Ctrl Enter. All right, so after we have done this, we go back to our notepad, and now we prepare the data for JAX. Okay, so we prepare the data for JAX. So let me copy this code. I would explain this code. All right, so this is what we're having here. So we're having all right, so the n here, we define n as n row, which is the number of observation rows, that is the number of rows in the data set. Here now we are extracting the required variables we need. So we define pre_test as data $sign pre_test underscore score. So basically we are just extracting these variables from our data. All right, so now we're having the group new here. So the group new, simply we are converting the groups. You remember the group, we are having a traditional and a new method here. Okay, from our console here we're having traditional, and then if you go down you would see the new method. All right, so we are converting them here under this group new here. So data $sign and dollar group. So the new group, new method here now becomes 1, and the traditional here becomes 0. So this is what we're doing here. So after we have done this, then we save them all under this variable name jags_data. So this combines all the data into lists to pass the jags model. So we do this here. We bring in the n, we bring in the pretest, we bring in the post-test and the group new, and put them as lists. Okay, so after that, so basically this is the explanation of this model here. So we click Ctrl Enter. So we are preparing our data for jags. Ctrl Enter for this. So let's start from the top. So Ctrl Enter, Ctrl Enter, Ctrl Enter, Ctrl Enter, and place them as list. Ctrl Enter. So having done that, we would go and pick the next line of code, which is to set up initial values for the parameter. So we are basically setting up initial values for our parameter. So I'll be explaining this code in R. Ctrl V. All right, so the purpose of this is to provide starting values for the parameters. Here for the parameters beta 0, beta 1, and beta 2, and tau as well. Okay, so now please note that good initial values can also help the model converge faster. Okay, so after which we click Ctrl Enter. Ctrl Enter. All right, so now let's move to the next line of code. Now we create the JAGS model. So we create the JAGS model here. Copy this to our RStudio so we can run it. Ctrl V. All right, so in creating the JAGS model here, we would use the function jags.model. Okay, so now we're having the text connection here. The text connection simply passes the model code. Okay, so we're having our data. Our data is equal to jags data, so what we prepared earlier. So this is exactly what we prepared. Look at it here, the list. So that is our data, and the end of chains tells us to run 3 parallel Markov chain Monte Carlo. All right, so we can call it MCMC. So, and this is to use the initial values defined earlier. So we have defined the initial values earlier here. So initial values, we define them as beta 0 equals to 0, beta 1 equal to 0, beta 2 equals to 0, and tau equal to 1. So we have defined this earlier. So we just Ctrl Enter to run this function, and after which we go to the next line of code, which is to run burn-in phase. Okay, copy this into R, Ctrl V. So the purpose here is to run the first 1000 iteration to allow the model to stabilize. So basically that's what we're doing here, to allow the model to stabilize. So now just know that the initial iteration are discarded to ensure the results are not affected by the post starting values. Okay, so let's quickly Ctrl Enter this. All right, so we are good to go. Now let's go to the next line of code. Here now we sample from posterior. So we sample from posterior here. We copy this here and we take it to R. So this function, the coder.samples here, draws samples from the posterior distribution for the parameters, okay? And if you look closely, we are looking at the posterior for beta naught, beta 1, beta 2, and tau. And the iteration here, number of iterations of the sample is 2000 here. All right, so to estimate the posterior distribution, basically this is the code we make use of, after which we click Control Enter. All right, so this is set. Now let us summarize these results and see how. So summarize results, and see what we get. So this is our results. Let me just make this a bit bolder for us to see. Alright, so this is our result here, and the empirical mean and standard deviation for the variable. So this is where we are going to make our conclusions. This is the result we're going to make our conclusions from. So from here you would see that this particular result shows the posterior mean, standard deviation, and credible interval or quartiles for this for the model parameter. So for the beta naught, we're having a mean of 7.14728. For beta 1, we're having 0.97400. For beta 2, we're having 4.80848, and tau we're having 0.09383. All right. So the beta naught is the intercept or a constant. The beta 1 is the effect of the prescore test. Beta 2 is the effect of the group. Tau is the precision, which is also inverse of our variance. All right, so let's quickly interpret these results. For the beta naught, we are having a mean of 7.14728. All right, and the standard deviation, this is the standard deviation. All right, so now the credible interval for beta naught starts from 2.60661 down to 11.9385. So which is that means the 95% probability the true value of beta naught will lie between this 2.60661 to 11.9385. all right, so that is that for the beta naught. So let's go to beta 1. Beta 1 is 0.9, the mean is 0.97400, and the interval, the 95 credible interval, is from 0.89922 to 1.0435. all right, so you can see that the interval here for the beta 1 is narrow, suggesting high confidence that beta 1 here is close to 1. So it's close to 1 here. That is for beta 1. Now the mean for beta 2 here is 4.80848, and the 95 credible interval is from 3.50837 to 6.0826. so this means that there is 95% confidence interval that the effects of the new method lies between this range here. all right, so now let's go to tau, which is the precision here. The mean is 0.09383, and the 95% credible interval is from 0.06969 to 0.1229. all right, so the credible interval confirms that the precision, from what we are seeing here, that the precision is small. Okay, so meaning that the residual variability, which is the uncertainty, is relatively high. So since the precision is small, the uncertainty of course will be very high. So to practically summarize these results here for the beta 1. So all right, so to quickly summarize this model here, we can see that the beta 1, which is the pretest score, have a strong positive effect on post-test scores, okay, from what we can see here. And also the beta 2 here, which is the new method, groups improves post-test scores by about 4.8 units compared to the traditional group. So looking at the intercept, you also see that the intercept suggests that the baseline performance for the students with the pre-score test, that is the intercept here, suggests this. What the beta naught, which is also the intercept, what is suggesting is that the baseline performance for students with pre-test score of 0. That is what this is suggesting the performance for students with pre-test score of 0. All right, so the tau shows the moderate uncertainty in the residual. That is this one here, shows the moderate uncertainty in the residual variability, which reflects unexplained variation in the post-test score. So basically that is what the tau here is telling us. So to conclude this, okay, from what we have in here, we can say that the pretest scores significantly influence post-test scores. And also we can also further say that the new method group has a clear positive effect on students' performance compared to the traditional method. So basically that is what our result here is showing and telling us. So that is it. So if you have any question, you can drop your question in the comment section. Okay, so do not forget to subscribe, like, and click on the notification bell so that you get instant notification when I upload new videos. All right, so we can actually visualize this our result. We can actually visualize it using a plot. So we can visualize this item here. Using this code here. So basically we just control enter this and adjust this so that it can be visible in our R. So let me do this. So we've adjusted it, and let's see what we have. All right, so these are the plots we're having. Okay, so if you need more explanation on how to interpret these plots, you can as well drop your comment in the comment section, okay, and I'll do well to reply you ASAP. So this is where I am going to be stopping for the purpose of this tutorial. If you have any question, like I said earlier, do not hesitate to drop your questions in the comment section. And if you want to know more about Bayesian analysis, you can actually drop your concern in the comment section, and we'll talk better and we'll see how you have a better understanding of Bayesian analysis. So thank you very much for watching, and for support, if you wish to support me so that I can deliver more quality videos on data analysis, you can as well reach me through my contact via the description. Okay, so thank you very much, and bye.